Welcome back. This lesson is about series and parallel relationships. When we use electrical power, like power tools for example, the electrical properties of volts, ohms, and amps share both series and parallel relationships with each other. So it is important that we understand what series and parallel relationships are if we want to know what's going on in an electric circuit. Let's start with parallel relationships. Properties share a parallel relationship when they are independent from each other. I like to think of parallel relationship as an analogy or a simile. Similes and analogies compare the properties of one thing to the properties of something else. You were brave as a lion, for example. Doesn't mean that you were actually a lion. It just means that you shared some of the lion's properties in that moment. Clear as mud, right? Series relationships are if-then relationships. If one thing happens, then something else can ensue. Electricity is a perfect example of this. For me, to use an electric drill, for example, I need to have some form of static energy or volts stored up somewhere. Then, and only then, can I hook up some wires and get some kinetic energy moving. Static energy and kinetic energy work in series to produce electric power, called watts. Let's take a look at this grid power system, for example. We have three independent power sources here: a coal and gas plant, a nuclear power plant, and a hydroelectric generator. These power generators feed the electric grid in parallel. Meaning, if one power generator goes down for any reason, like maybe it caught on fire or maybe just a maintenance shutdown, the other two plants still run business as usual. The power plants run independently or in parallel to each other. However, in this electric grid utility system, there is also a transformer in series between the high voltage grid and the medium voltage grid. If that transformer is not sized correctly and catches on fire as a result, then all those low voltage customers are in the dark with no electric power. The series relationship between the high voltage grid and the low voltage grid makes the customer dependent on the transformer. Okay, now that we understand the difference between series and parallel relationships, next we're going to talk about series resistance, or points of resistance in an electric circuit that are in series with each other. The total series resistance is simply the sum of all the individual resistances. In this example, our load has 40 ohms of resistance, and the switch is adding 4 more ohms to the circuit. So our total circuit resistance is 44 ohms. In this example, if we account for the resistance in the wire, the total circuit resistance is 56 ohms. Table 8, Conductor Properties, is right out of the National Electric Code Book. In this table, the resistance in ohms per 1,000 feet of wire is given. You can also look it up in kilometers if you're using the metric system. Notice that as the wire size increases, the amount of resistance to the flow of electricity in the wire decreases. Remember Ohm's law. Ohms and amps have an inverse relationship, meaning if I want more current to flow through the wire, I need to do something to lower the resistance of the wire, like choosing a larger size wire, for example. Also notice that aluminum wire has quite a bit more resistance than copper wire does. The results of getting this wrong can be devastating. Look for my wire sizing class. This class is a prerequisite for it. In the next lesson, we're going to talk about using what we've learned to troubleshoot electrical systems. See you there.